हेलो।
हाय।
तो आएगा नहीं आएगा रे?
वसंत आएगा। और कितना क्लास बाकी है?
मेरा तो वैसे तो घंटा के हिसाब से बहुत क्रॉस कर गया है,
हम्म।
जितना शेड्यूल था।
हम्म।
बट एक दो क्लास और ले लेंगे, एक आज ही पढ़ाएंगे, बाकी दो दो क्लास प्रैक्टिस कर लेंगे बस।
हम जरा वेडनेसडे को दिन भर थोड़ा डीपी देखे थे। टाइम उसमें लग रहा है और ग्राफ भी देखना है, मतलब अपने से हमको बहुत सारा टाइम अभी स्पेंड करना पड़ेगा इस पे।
हम्म।
प्रैक्टिस करना
कल कल
पड़ेगा।
तो फिर कल कर रहे हैं हम लोग वो काम, क्रॉस ओवर।
अबे कल हम एक शेड्यूल करा लिए हैं, रात में कर सकते हैं।
चल ठीक है, कल रात शुरू करेंगे, ठीक है।
हम मतलब दो दो बजे जाएंगे तो शाम तक आ ही जाएंगे, रात को आ जाएंगे तुम्हारे यहाँ।
ठीक है तो।
हाँ। अबे एक ये एक अरे बाद में बोलते हैं।
बोल बोल बोल।
एक एक तुषार रो है, उसका भी वीडियो सही है बे। देखा है?
वीडियो?
हाँ, लेकिन वो टॉपिक मतलब एक प्रॉब्लम सॉल्व करता है हर वीडियो में।
बहुत सारा वीडियो है ऐसा। अच्छा अच्छा, अगर सिर्फ वीडियो से पढ़ना है तो बहुत अच्छा वीडियो
हाँ, तो उसका हम
है।
एक देख रहे थे, टाइनी यूआरएल का डिजाइन का, एक ही डिजाइन का प्रॉब्लम सॉल्व किया टाइनी यूआरएल का।
ओके।
तो बढ़िया बताया। हम जैसे सोचते हैं तो सिर्फ इतना रहता है कि हाँ, कोई लॉन्ग यूआरएल आया उसको शॉर्ट करके कहीं डीबी में स्टोर करेंगे या मैप में, या फिर उसको रिटर्न कर देंगे।
ठीक है।
मतलब वो सब कुछ बोल दिया भाई कि सीडीएन डालेंगे, फिर से 5 डीबी रहेगा तो कैसे, मतलब नहीं जो लॉक वॉक नहीं लगाते हैं कि कॉन्फ्लिक्ट नहीं आए। फिर से
हम्म।
जू कीपर में काउंटर मेंटेन करेंगे। बहुत
हम्म।
बढ़िया से बताया था पूरा, कि 2 डीबी रहेगा, एक में राइट करेंगे बाकी में रीड करेंगे, सिंक होगा, बहुत कुछ मतलब अच्छा से बताया था डिजाइन के। तो हमको थोड़ा सा आइडिया लगा कि ये सब चीज हम लोग को भी पता है,
हम्म।
लेकिन आंसर करते टाइम साला अगर कोई टाइनी वायरल पूछ दिया तो हम लोग चाहेंगे तो 30-40 मिनट खींच सकते हैं एकदम बढ़िया से उसको डिटेल में बता के।
समझ।
पैसेंजर वैसेंजर लोड बैलेंसर सब कुछ बोल दिया वो।
हम्म।
तो ये सब बोलना पड़ता है, नहीं मतलब हमको नहीं
हाँ,
पता था ये चीज़।
डिपेंड करता है किस लेवल पे इंटरव्यू है। अगर
हाँ, ये भी
इंटरव्यू
बात सही है।
H1 का है, H2 का है, H3 का है, तो उसी लेवल पे आंसर भी आना पड़ेगा।
वही डिजाइन राउंड अगर बोल के लेगा तो ये सब चीज बोलना पड़ेगा, प्रॉब्लम सॉल्विंग रहेगा तो इतना बोलने का क्या जरूरत है।
हाँ।
प्रॉब्लम सॉल्विंग में तो हमको लगता है बस एनक्रिप्शन का ही होगा, एनकोडिंग का टेक्निक, कि कैसे
हम्म।
एनकोड कर सकते हैं।
हम्म।
अजीब पढ़ा रहा है।
अंदर है क्या? आई नीड ईयरफोन। आई नीड ईयरफोन, वरना आवाज करेंगे। ईयरफोन? उनको ईयरफोन दो वरना आवाज करेंगे। इसमें वो है माइक है? नहीं, वो है माइक। वो तुम ईयरफोन आवाज नहीं करना है। उनको आवाज नहीं करना है। दोनों के पास हो जाएगा। अंदर क्रॉस लेवल है प्रॉब्लम वाई सर प्राइस मत दे दे कोई नहीं साथ यार तो ये है मैं हाई देना है आ गया और क्लास होगा ना वीडियो खाना भी गया है
Hello. Okay, let's start then. Vasant?
Yes.
Okay, we'll start. Nitesh, mute.
Yeah, done.
Okay. Yeah. So we'll be covering Heap today, which is one of the last data set we'll be covering. And then few more classes we'll be only doing some practice. That's it. Okay. No, so Subhadeep and Athar are not here today, so we'll try to cover only Heap and nothing else. I plan to do something more, but let's cover at least Heap today. So we again, just to repeat what all we have read is we started from array, simple array, then we went ahead with linked list, then double linked list, queue, double indented queue. So we covered all the linear data structure. Then we talked about non-linear data structure, tree. In that tree, we talked about binary tree and all those different kinds of tree. We talked a little bit about the height balance tree as well, which is a AVL tree. We did not talk about red black tree or AB tree on all those. I can go through those, but they won't be. You can expect no question, but they can ask you, what do you know? What is a AB tree and what is a red black tree? So I'll cover those topics. So AVL tree we have covered, and I'll repeat. AVL tree is same as height balance tree. Okay. So after that we talked about graph. We had almost 5 lectures on graph, and then we talked about yes, that's it. So now the last topic is heap. So we start with the representation of the heap. So first of all, what heap is something similar to a queue in the sense that we have a queue which is also containing priority. So every queue, every element in the queue has some priority, and hence we call it a priority queue. So the one with either with a maximum score, minimum value, or anything, that is, we decide a priority on any value, and based on that priority, it's stored in such a way that the most prior element is at that we can fetch the most prior element fastest. Okay, so in an array also we can keep them in a sorted way, and then sorted based on the priority we can store them. But the problem would be maintaining the most prior at such a suitable position that we can fetch the maximum priority element in constant time. So that's the problem in maintaining priority in an array, in a simple array. So that's why this is where heap comes in. Heap is a priority queue. So if the term is it's one of the priority queue. Either we choose a minimum as a priority or maximum priority. Both of them are decided, like we can decide earlier whether we want to call as 1 as priority or 100 as priority, whichever like maximum. So depending upon whichever priority, either we have a min heap or a max heap. So for in a min heap, the most prior element will be the minimum element with the minimum value. So if you see here, I have drawn here 2 heaps. If you can see, this is on the left side we have a heap. 10 is the topmost element at the root, and the children of 10 is 20 and 100. So 20 and 100 are greater than 10, hence they have less priority. So they will be coming after 10. Okay. Similarly, we have one more heap written here. This is also one of the mini heap, and this is, as you can see, this is the structure is same as tree. So one line I have written here is complete tree. So you remember what is a complete tree, Vasant?
Yes, Praveen.
So what is a complete tree?
The difference between last node and its previous node should be 1.
Okay, the difference between last node and previous node should be 1. Can you just
The
make
height.
it like
Oh, yeah.
the
And
height?
yeah,
No, I didn't get height of.
the height of the last node and the previous node should be 1. Like last and last but 1.
No, I haven't.
Otherwise, it is
I
like
haven't.
if it can have the last node can have one left node, and it can have, or it can either have 2 nodes or 1 node. The last node means
No, what you're trying, although you saying wrong only, but still what you're trying is something called height balance and not this. Okay, what you're trying to say is the height of the left subtree and height of the right subtree differ by at max 1. That is a height balance tree. Okay, but still, I'm talking about a complete tree. What is a complete tree? So complete tree is a tree in which every node has 2 children. Every node
Except
has
the
2, except the last level.
last
Except
node.
the last level. Okay, except the last level. In the last level, we can have missing nodes. But one more constraint is that it will be left filled. Okay, so if you can see this, we have 10 has 20 and 100, 20 has 30. So this is a left filled. So the next node, if the next node we want to add, that will be just after 30, like beside sibling of 30. It will be 40, and it cannot be a child of 100. It has to be child of 20 only. So this is a complete tree. Every level will have 2 to the power I level of node. 2 to the power every ith level will have 2 to the power I nodes, and the last level can have less than that, but only that one but with a constraint that it will be left filled. Okay, so that is a complete tree. And why I'm talking about complete tree, because a heap is always a complete tree. Okay, so whenever we add a node, we have to ensure the completeness of the tree. We can add or delete, whatever you do, just ensure that it is a complete tree. Along with the another property that every node will be the child of each node will be less priority. Okay, so let's just concentrate on min heap only now. Okay, I'll talk in terms of min heap. So what do I want to say? I want to say that the property of each node is that the children will be bigger than the current node. So that is the property of a min heap. If you talk about max heap, the value of the node will be more than the children node. So that is in the max heap. So in terms of priority, the priority of the root node will be more than the priority of the children. That is what priority heap is. That is what a heap is. Okay. If it is a min heap, then the value of the node will be minimum less than children. If it is a max heap, then the value of the node will be more than children. Okay. So this is a min heap and max heap. Now, if you satisfy these two property, that one is the priority property, the priority of the node will be more than its children, and second is it is left filled complete tree, then that kind of representation is a heap. Okay, we can represent by this structure. So Subhadeep,
Yeah.
so we are talking about heaps today, and what I've told till now is what a heap is. So heap is one of the data structure which is used to the biggest advantage of using a heap in anywhere is fetching the most prior element in the least time, in the constant time. That's the use case of a heap. So, and how do we maintain that? Is we create a tree kind of structure of all the elements where two properties are satisfied. One is that it has to be a complete tree, and second is the value of the node will be more prior than the value of children. Okay, these two properties satisfied in a tree is called will be a heap. Now we're going to do the implementation. So if you remember, we tried to implement in our early classes, like initial classes, we tried to implement queue or stacks using array. So this is again we are going to use the array to implement our heap. Okay, so till now whatever we have just said is priority of a node will be greater than priority of children. This is one property. And second property is the tree should be complete. Okay, so if we take this tree, take this heap, the leftmost heap. If I want to store this in some data, suppose array only, the first element will be 10, second would be 20, third is 100, and fourth is 30. How I'm doing this, I'll come to that. Let's just store the second heap also. Okay, so first element is 10, second is 15, and then 30, and then 40, 50, 100, and 40. Okay, so what I'm doing is let me open the slide one. Okay, so can you see the slide?
Yes.
Yeah.
Yes.
So if you see here, this is a heap which is implemented using an array. Okay. So if this is a root element, 11 is the first at the first index, which is 0 index, and then both the children 17 and 13, both children are the next element, so 17, 13. And if you see that there these three property, every node. Okay, if you try to find the parent, so just pick any random node. Let's suppose 18. So if you try to find the parent of this node or the fourth element, the parent of the fourth element will be I by 2th element, which is second element. Just see that. Is it correct? So if we store it in this fashion, that 11 is the root element, 17 and 13 is the next two element, 18 to 21, 19 and 17. This is level or traversal. If you see, this is level or traversal. Okay. So 11, 17, 13, 18, 21, 19, 17, 43, 23, 26. Okay, this is a level or traversal of this tree. And once we have stored this value in this array, if you try to find the parent node, how will you find the left child? It's like simple, like node dot left, node dot right, and node dot. How can you do that? To do all those operations, you simply have to run simple index operations, which is like I by 2, 2i and 2i plus 1. So let's again go back to this 18. So what is the parent of 17? We can see here, if you see here, the parent of 18 is 17. Okay, this is the parent. And we can get that by the returning just the I by 2s element. Return I by 2s element, you'll find the parent of ith element. How to find the left child? The left child will be at 2i index. So if the index of element is I, the left child will be at 2i index for sure. So just try to analyze this, how it is happening. You can try to do for any index and then see that this property is being followed everywhere. Similarly, the right child will be at 2i plus 1th index. So let's talk about 21. What is the index of 21? 21 index is 2.
5.
Sorry, 5. Okay. 21 index is 5. Now 5 has left child 26. And what is so if I want to find the left child of 21 will be 5 into 2, 10. So what is that 10th index? 26. So this property is followed for every node in the if we try to implement our heap using in this array. Now with this storage, just a minute. So with this storage, we can perform all our operations, insert, delete, and find minimum and all those. Yes, Subhadip, go ahead.
So for 21 the index is 5, correct? So
Yes.
for that the parent is 17, which is at index 2. Okay.
5 by 2, yes. 5 by 2, which is 2.5,
So
but
we'll consider the lesser.
we take the floor, yes.
We'll take the lesser, not the greater, like 3.
Yeah, floor. In terms of mathematics, floor. We don't take the ceiling, but the floor,
Yeah,
yes.
okay.
Okay. Okay then. So with this structure, we'll try to implement our insert, delete, find minimum, and all those. Okay.
Praveen, here one question. You said floor and ceiling. Floor means it is going to take the lesser value, or what is that?
So 2.5 floor is 2 and ceiling is 3.
Okay. Means here we need to take floor.
Yeah.
This implementation.
Yes. Okay. So coming back. So before I go ahead with the insert and all, we'll try to write a code for our heapify, which is one of the most popular keywords sometimes whenever you talk about heap. What is heapify? Heapify is a method to build a heap. Okay, given a random tree, we can convert into a binary tree heap just by doing by doing multiple heapify operations. So what is heapify? If you take a tree representation, suppose you have this heap, okay, and given that this 10 was somehow misplaced, that this value was suppose 35, okay, so this is not a heap right now. Why? Because 35 is not the minimum element, but still it is at the root. So we have to ensure that this is a heap. So how can we do that? Is we can perform a heapify operation at the wherever this is not following the property. So the first node which is not being followed here is 35 only. At 35, both the children are smaller. So this means 35 cannot be the root. So we can perform a heapify operation. Okay. So let me just write a heapify operation, then we'll do a try run over here. So what we do in heapify is heapify is performed at an index I for array A. Okay, for array A means the A is the array which we have used to implement our heap. So we have to perform heapify operation on array at I as index. Okay. So what do we do is we check if okay. Hello.
Hello?
Someone joined and left. Okay, leave it. So I was talking about heapify. So what do we do in heapify is we start from the ith index and we compare with both the children. We compare with both the children, and if both of them are, again we'll just talk in terms of min heap and not, we won't be confused about min or max. Okay, so if both the children are bigger, are greater, then we stop there. We don't have to go ahead. But if it is not less, if the node value is not less than the children, then we have to bring that node below. Like we have to move that node below the children. So we have to swap the values. So if we talk about, let's just again go back here. So we have 35 is bigger than 50 and 30. So we have to bring 35 either below 15 or below 30, but either below either of them. Okay. So that's what we'll do. We'll compare with the children and then compare what is the value of left child, right child, whichever is bigger will go below. Okay. So let me just write here. So if A of I is less than A of left child. So where is left child? Where is the left child?
2i.
2i. 2i. If A of I is less than this and A of I is less than right child,
2i plus 1.
2i plus 1, then we do not have to do anything. That is it. We're done. Okay. Otherwise, So check which is greater is equals to ith. Suppose I assign ki I is the greater element, and then we compare if a of I is more than a of 2i, then if a of I is more than smaller, we compare with left and also with right. Whichever is bigger, I have to swap a I with that greater. So what we'll do is okay. So what I'm doing here is I'm just assuming that the smallest element is at ith index. Okay, so which might not be true, but I'm just assuming here. And then next line I'm checking if a of I is more. If a of I is more than 2ith, then the element at 2ith is smaller than this. Okay, I'm just assigning keep maintaining which is the smallest. Okay, which is the smallest which should go at the top. So right now I have assigned the value at ith index is the smallest, and then I compare with the left child. If left child is smaller, if a of 2i is smaller, then we can say that element at 2ith index, which is left child, is smaller than ith index. Similarly, I compare with right child as well. If is ai 2 plus a of I 2i plus 1, a of 2i plus 1 is less than a of I or not. If it is, then that is the smaller. So either one, it can be like case that both of them are smaller. Okay, but we have to find only one of them. We are okay with bringing root node either in the left subtree or right subtree, but we just have to bring it down. That's the only thing. So we just check both of them, whichever is smaller than ith element, whichever is smaller than the root element, the node element, we just swap that with the ith element. Okay, so this part of code. If you're getting confused, I'll repeat again this one again. So I just have to find among both the children, left child and right child, which one is smaller than the ith element. Okay, anyone I want to find. I'm just doing is I'm comparing with left child. Is left child smaller? Yes, then assign them as smallest. Is right child small? Yes, assign that as smallest. Okay, so and one of them will be smaller. Why? Because we already ignored the last case. We have already ignored that no one is smaller than ith element. So we have already ignored that case. So hence one of them will be smaller. Whichever is smaller, I'll just swap. Okay, I'll just swap that with the ith index. Okay, now after swapping, I will call this method recursively. I'll call this method recursively at that smallest index. So either at 2i or 2i plus 1, any one of the place. We'll call it again. Okay, so confusion, anyone? Subhadeep,
Yes.
confused?
ना समझ में आया.
Okay.
मतलब
So
मैं जो समझा
see, there are people who do with a small, greater and
swap
greatest
कर
and
रहा
all.
है
Yeah.
चेक कर रहा है swap कर रहा
Okay. So if you come to again this representation, so we started from this 35. So 35 was here. We compared 35 with 15 and 30. Okay. So we just replaced. We brought 30 here, and we brought 35 here. That's the first. So यहाँ पे 30 यहाँ से 30 यहाँ आ गया and 35 यहाँ आ गया. Now we'll call recursively on 35. So again with 35 can either go below 100. No, it can't. Can it go below 40? No, it can't. So it will stay there only. So we'll stop there. But it would. But suppose if it was again 32 only, then 35 would compare with left. It cannot go below left. Will it go right? Yes, it can. It will go below right. So again we'll swap 32 and 35, and then again we'll go ahead. Now it said no children, so no more swapping and no more recursive call. Okay. So at the end, what happens by heapify is heapify called at ith index ensures that the value at ith index, if it is not satisfying, it will bring it down to this correct position and then stop there. That's what the heapify method does. Vasant? Hello? Vasant?
Praveen, this is max CP5, correct? Whatever is it.
No, this is a minimum heap. There's nothing called max heapify. There's only one thing. I mean, you can call it min heapify or whatever. This is heapify in a min heap. Heapify in a min heap.
Okay.
So this is heapify. If you want to name it, yes, you can call it a min heapify because it's a heapify in a min heap. Hence, it's a min heapify. Okay, but a better way to call it, it's a heapify in a min heap. Okay.
Okay.
So everywhere you can simply do instead of just talking about, if you want to talk generic, you can compare if the priority of the left element is less than priority of the right element. Here we are comparing the value because we have priority is value. But if you talk about very generic statement, would be priority of ith element is less than priority of jth element, something like that. Okay, that is what we want to do, priority, not just the. This is priority a little bit confusing. That's why we come down to either min heap or max heap. Either the minimum is a priority or max is a priority. Okay. Okay. Moving ahead. So we have implemented our min heapify. Now using this method heapify, we'll be able to do other operations. The next operation is remove minimum. So you have to think and apply your logic. How will you do this? So you have what you have to do is given a heap, you have to remove the minimum element. How will you remove? So you have to delete the minimum element. So first of all is finding and then deleting also, and delete in a way so that your the remaining data set is still a heap, still a proper heap. Okay. Got the question? Problem?
No, can you please repeat?
So question is, you have to delete the minimum. What is the, we have been studying till now, the remove minimum or get minimum from a heap is a constant time operation. We always do this. Remove or finding a minimum element from a min heap is a constant time operation. Okay, that's what you have to do. Finding a minimum is constant time, but removing a minimum is log of n time. I'm just giving you time complexity also. But that's what you have to do. You have to delete the minimum element from a min heap. I'll repeat the question. Delete the minimum element from a min heap. You have been given so now I'll write a signature of the method. You have to implement this method. I'll be back in 2 minutes. Okay. So you have to void delete minimum from a min heap which is stored in array A. Done. Okay. Any question?
No.
And you can use the heapify method if you want. Yes. Nitesh, कुछ सोचा?
We can replace the root of the heap with leftmost node, and then we can call heapify method, right?
Okay, so you're correct. So what we can do is we have to delete the value. So what we can do, we can copy the value. So it's difficult to delete from middle. What I meant to say is it's difficult to delete from the topmost element or the middle element. It's easy to delete the last element. If you see in this heap, 10, 20, and 100 and 30, deleting 30 means just decrease the size of the heap by 1. If you implement an array and you maintain the size of the heap, if you simply just decrease the size of the heap, this element is anyways ignored. So deleting last element is an easy way, but deleting something from between the heap or from the topmost element is a tough task. Why? Because we are representing an array, and if you delete something from between, all your property of 2i 2i plus 1 I would be wrong. So we have to maintain that property, that parent of I will be 2 I by 2, left child will be 2i, right child will be 2i plus 1. All those things we have to maintain. Okay. So that's why deleting from somewhere between is a difficult task, but deleting from the last position is the easiest way. So we'll use this fact that deleting from the last is very easy. So what you can do is you copy. So we want to delete the minimum, which is at the topmost element. How do you do is you delete the last element. Okay, that done. And sorry, not delete, but you take the value from the last element and delete the last node and copy that value at the topmost value, at the topmost index, the zeroth index. Now, once you've done that, your property, you have one property satisfied, that is still leftmost filled, but that property of minimum that node will be less than children is wrong now. So you have to correct that. How can you do that? You have to call heapify at that I, as simple as that. We have discussed the heapify method. We simply called heapify at the ith index. Okay? This is very simple. Okay? Subhadeep?
Yeah.
Yeah. So now you're done heapify. Let's do about insert. How will you before insert? Tell me remove decrease key. Okay. How will you implement decrease key? So there's a node whose value is 50. I want to change it to suppose 12. How can you decrease the key?
You want to change the value itself.
Yes, change the value of the node from 50 to 12. That's it. Update a node.
So we can update and then call heapify on that.
Update 50 to 12 and then call heapify.
Yeah.
So Pradeep, update and call heapify on that index. Is this correct?
Yeah.
No. So heapify brings the value down. If you see it brings the value from ith to some either 2i or 2i plus 1, like that. It brings the value down. It brings a parent node to downwards. But here you have the value decreased at 50. From 50 it became 12. So how will you bring it down? Like you will move it down only. Where will you move? It can't go down. You have to move it upward somewhere.
Yeah, upward.
Understood?
Yeah.
So there's something as similar as I don't know why they didn't give it terminology called heapify or something, a reverse heapify. So you just simply do a reverse heapify kind of thing. You compare with the parent. Okay, if the parent is smaller, then don't do anything. If parent is bigger, just swap with the parent and keep on doing it until you don't break this property. So just compare with the parent, and so you do, if a of I is less than more than a of 2i, don't do anything. If a of I less than, then swap I and 2i. I and I by 2, and then repeat the same thing recursively till you reach the this property, till you reach the point where this property is not broken. Okay, understood what I said just now? This is something reverse of heapify. You're not going down, but you're taking the element. Only one element has been changed. Okay, so we know that only this element, only this value is not a correct place. So we have to move this value to correct place. How can you do it? So you are decreasing. We are decreasing. We are not increasing. If you had increased, we could have done something else. I'm talking about decreasing. So decreasing के तो ऊपर जाना है क्योंकि min heap है. Again, we are just talking about min heap. Okay. So since this value we have decreased, so this makes sense to go up. How will take up? So we'll call this method, which will just move it up by one by at from I to I plus 2th I by 2th position, then again I by 4th position till this property is broken. Okay. ठीक है.
Yeah, here one question I missed. What is the thing you are putting into array, right? Everything is in array. Is that array or what?
Yes. Everything is array.
Even while doing max means min EP5, that time also we are doing it in array itself. We are checking everything.
Yes, everything is in array. Yes. So decrease key is something opposite of, I was saying, heapify. What we do is we compare the value at I and the value at I by 2. Why I by 2? I by 2 is the parent of I. So if the value at I by 2 is less, okay, or more, depending upon that. So this is a min heap. The value of parent has to be less. If it is not less, then move that move the element, swap the element from at I and I by 2, and then go ahead till run this while loop till this property is not satisfied. Okay. Till what property? Till the property that value at parent is less than value at children. Till that point of time, keep on going up while loop, and then just replace swap and then go ahead. Okay. समझ में आ गया?
हाँ.
Confusion? Vasant?
Okay. No problem.
No. So what was heapify? Heapify was like start from ith element, you compare with children, and then you decide whether to move this element down or not. Okay, that is heapify. In this case, what I'm saying, decrease key, what I'm saying is we compare with the parent. Okay, we compare with the parent instead of children. We compare with the parent. Why? Because we have decreased the key. Then it makes sense that since this is a min heap, the value should go up the tree. And how do we move up the tree? We compare with the parent. So value which we just decreased. So we started with this earlier value. Earlier this value was 50, but we want to change it to 12. So we want to change 12 should move somewhere else. Where should it go? Since we're decreasing, it should go up only. Hence, yes. So 12 will compare with 50. Is it less? Yes, it is less. By the way, this was 10. Okay. So 12 will compare with 15. Is it less? Yes. So 12 and 15 will swap. Now again, I'll compare 12 with 10. Is it less? No. So that's done. The while loop will stop here. Otherwise, just keep on going up. Do this while loop while array of I by 2 is greater than array of I. Do what? Just swap I and I by 2. Keep on doing this. Swap this and then I equal to I by 2. Correct? बस यही करना है while loop. So we just keep on moving one step ahead. One step up, I mean. ठीक है, वसंत?
Yes.
Okay. Yeah, so I'll move ahead again. Now the next is decrease key, insert key. So insert a new key. You have this heap already given, which is 10, 12, 15, corrective, and you want to insert 20. How will you insert? Tell me the method to insert.
Insert at any place or means given place, right? We are going to give some place, height position somewhere.
No, so insert at its proper place.
No. Initially, we are going to give some condition, right? Insert at some.
No. We have this heap, or which is stored in this array A. We have element from at all the indexes. We have element at 0, 1, 2, 3, 4, 5, 6, 7, 10 index. We want to insert new element. So and that you have to find where to insert and all, but you have to implement. I mean, there's no position given. You just have to insert. But
Okay.
by the way, before we do insert, we haven't talked about the time complexity of all these methods from the beginning. Okay, so just implement this insert now. We'll talk about time complexity as well. Okay. So you have to insert a new element 20 in this heap anywhere, which is the correct solution, which is the correct position you have to find and then insert there.
So what we can do here, we can find out the last position, like finding the length of that array. So
Length of array is given. It's
okay,
given to you.
then we need to add length of array plus 1. Then there we can insert a new element. From there we can do this condition, whatever that reverse mini if something, whatever.
Yeah. This same thing will just run. So everyone understood what you just said. So we have this heap where we have elements stored from 0 to nth index. If we want to insert the next element, what we simply do is we put it at the last place. Okay, and so in terms of array I'm talking about, we put it at the n plus 1th index, and then we simply call this method while a of I by 2 is more than a of I, and keep on swapping till we satisfy this, until we do not satisfy the heap property. The moment we satisfy, we just stop there. Simple.
Yeah.
So what is the time complexity of this insertion?
Order of height of the tree.
Nice. Order of height. Yeah, order of height of the tree, and which is
login.
Yeah, login.
Nice. Where n is
Number of
nodes. Number of nodes or number of
yeah, correct.
Number of elements in it.
Elements in the array.
Yeah, correct. So what was the time complexity of delete?
Order of height of the tree. Again, swap is doing.
Same. Yeah. What was the time complexity delete minimum?
2 of 1 if it is no log n only.
Log n only. So all the operations are log n except the remove find minimum, which is constant time. Rest all the operations are log of n only. Okay.
Yeah.
This means like changing the value. The last one you explained. Always we need to change, means reduce the value. We should not increase the value. Then it will be wrong, right?
I didn't get come again.
So like the previous explanation you told us, like in order to change the value any node, so always we need to input smaller value compared to the current value. Is that correct? Assume if it is 15, I'm going to replace 15 with 11. I should not replace 15 with 20. Is that correct?
No. So no. What you're saying is, I gave you a task. Implement how will you decrease the key. If you want to implement how will you increase, you can implement that also. The question was you have to decrease. How will you decrease? If you want to implement increase key, that you can do by increase also. So how will you increase? Suppose you want to change the value of 32 to 39. How will you do? Increase key, how will you do? You want to increase the value of 32 to 39. So by increasing the value, we can increase simply 32 becomes 39, but that will violate the heap property. So what will you do? You have to move it down somewhere. In that case, you have to call heapify at that ith index. And if you decrease the value, you have to call a reverse heapify, which is again, do not say this term reverse heapify. Haven't seen this term ever. So you have to call this method where you move the element up the tree if you decrease. So just a generic language is move the element to its correct position by moving up or by moving down. Okay. How do we move up? By we compare with the parent, and where is parent? Parent is the I by 2. Okay. And how do we move down? We compare with the children, and where is children? Children is at 2i and 2i plus 1. Okay. Okay. So we have done all the basic operations. So let's take a question now. Before I take a question, so we have heard about heap sort and how does heap sort work. Can anyone tell me how does heap sort work and what is the time complexity of heap sort? So given an array of integers, how will you sort that using a heap?
We need to do heapify.
Heapify, so you need to do a lot of heapify. So tell me complete end-to-end solution. How will you sort an array of integers using a heap?
The mean heap will always guarantee the root is minimum.
Correct.
So we can remove the root and then again heapify the heap.
We can remove the heap. That's it. What do you, the remove heap is doing it
No,
by itself. What?
no, we can remove the root.
Yes.
So the minimum we have picked, and then we can again maintain the heap.
Yeah. So yes, you're correct. So first thing is just store everything into the heap. Okay, and then keep on just removing the minimum one by one. So first step is store all the values into the heap. Transfer all the values from array to the heap. Okay. By the way, what do you mean by transfer? Why do we transfer only? We can simply use the same array to construct our heap from this array. Understood?
Yes.
So whatever, like we'll not go there right now. We're just thinking we have this array of elements. I will just construct my heap first, which is insert all the element into the heap, and then once the heap is constructed, I will delete a minimum one by one till all the elements has been deleted from the heap, and the order in which we get is the correct order. So what is the time composition now? So first is constructing the heap. Second is deleting the heap n times. Every time we delete a heap, something happens. So what is the overall complexity? Can someone tell me? Calculate, not just to calculate. How do we calculate this?
I missed that.
So I'm saying to do a heap sort, what we're doing is we try to build a heap first from the given numbers, and with that number, with that sorry, so with that heap which we have constructed, we just try to delete the minimum one by one, and at the end we have deleted all the numbers from this heap. We have this array of sorted number again back. So there are two parts. One is constructing the heap, and second is deleting the minimum element n times. So what is the total complexity, overall complexity? Tell me the complexity, and as well as how did you calculate?
See, deleting it takes log n, and we are doing it for n items, so n log n.
Yes, correct. So
Yeah,
deleting
log n.
yes, n log n is deleting n times, and every delete is log n, so hence it is n log n, correct. And how much was constructing?
Order of n.
Constructing a heap is order of
N.
how? No random guess. Think how will you construct? So we have an array of numbers. We can just simply take one by one each element and put it into our new heap which we are creating. Take element, put in the heap. Take next element, put in the heap. So we'll do n insertions. And how much is each insertion? How much
Log
is
n.
each log n? So total insertion time will also be
N log n.
n log n. So total time will be n log n plus n log n, which is equal to 2 log n, which is
N,
equal to n
N
log
log
n.
n.
So we can heap sort an array using an array in time in order n log n time. ठीक है? Correct? Okay. So let's move ahead, and I have a question now, which is a very standard question, which is a lot of time this question gets asked is suppose in Amazon or in Flipkart, every day lots of products get sold. Okay, millions of products get sold. You have to tell the top 10 selling products of today. So what you have is product 1 got sold 10 times, product 2 got sold 100 times, product 3 got sold 93 times. You have the number of times each product got sold. Okay. Now you have to tell the top 10 products or top 100 products. How will you find top 100 products? ठीक है, समझ में आ गया क्वेश्चन?
Yeah.
Yeah. Okay, take your time then. I'll be again back in 2 minutes. ठीक है?
Hello. Hello.
Nitesh, tell me.
So we need to find out top 100 selling products, right?
Yeah, that is the thing Praveen asked us. Like we need to find out top 100, top 10, right? Top 10 selling products.
Okay, top N. So I think we can use Maxip, right?
Yeah, that is the thing. Yeah, we can use Maxip. Then it is going to
And
give
then
ascending order. So
whatever is required, we'll remove that much.
once it is ordered, then we can take the top 10 or top 20. We can iterate the top 10 elements.
Yeah, so we'll all the time we'll have to remove the root because only root will be at the correct position, right?
Yeah, that's correct. Here, my question is once we remove the root, then again we need to do this
Yeah,
EP,
correct, correct,
EP5
correct.
something we need to do, right?
Yes.
Yeah. So the
That one,
delete is login.
yeah, that one we need to understand how to do that. At least pseudocode type. We need to see where to call. Once it is removed.
So how it works, right? Uh, we'll remove uh, we'll remove root and copy the last node to the root and then call hippify on the root.
Yeah, that's correct. Maybe that is the thing. Again, it will yeah do downwards EP5. Yeah, that is the way. Tell me one thing, how priority key works here? Like, are we using queue here, or this is nothing but a priority key? Heap is nothing but a priority key. What is the thing?
Yeah, that's what Praveen said. Heap is the priority queue. So
Okay.
always the parent is the priority, not the child. So parent's position is always correct.
Okay. Are you preparing every day or what, man? Hitesh and Subodh.
No, dude, I'm not able to prepare nowadays. I'm not doing assignments also.
Me too as well. Like, I got into new project. It's totally hectic. I don't know what to do.
But I think I'll have to do a lot of DP and graph. Yeah, I understood, but 5, 6 problems minimum we'll have to do to like get the clarity.
Yes. But as Praveen said, I don't know what is going to ask in graph. In interviews, I'm not sure. Maybe they'll ask some basic
Now,
thing.
whatever Praveen covered, no, one of my friend went to Expedia. They asked the same similar questions, and DP also whatever like he said, they asked like 1 or 2 questions from that in
Okay.
Expedia.
Means how they asked, like they asked us, asked your friend to implement it or write a pseudocode, or what is the way they
No,
asked?
the DP and all that nowadays like in India and machine round also they are asking DP,
Hmm.
but after machine round they'll ask to write on a paper. So there like if you write pseudocode confidently,
Hmm.
then it's fine. But if you're not confident, they'll simply say like write the complete program and
Oh,
then dry run.
okay. It depends upon interviewers. Like if they get to know
Yeah.
confident, then
Dude, I have been listening to you guys. I've asked you to solve something, not to discuss right now. Okay. So, hello.
yeah, good.
So, question. I gave you a question. What about that? You're discussing your complete life. What about the question? Find the top 10 selling product, top 100 selling
We can
products.
use max heap,
Okay, and then
then remove 10 times like the root, the delete 10 times.
so you're saying you want to store all the elements in the heap.
Yeah, if
I
the
see
number of
you.
elements is too big, then heap, I mean the memory issue might come.
No, that is all right. What will come to memories? But what is the time complexity? You will store all the elements in the heap, and then
Then we can delete the root. So the root will be the max, right?
so what is the time complexity?
Deleting login as usual.
And 10 times if we delete, then 10 login,
10
that is
login.
login. The
What
login
about the
of
insertion? What about the insertion?
Order of n. Order of n plus login.
N plus login.
why?
Creating a
We
maximum.
just so we are inserting
No.
n element. We are inserting n elements, and every time
That
we
is
try
n
completing
login.
n login. So total complexity n login plus 10
Login.
login,
Plus,
which is equal to n login.
yeah, total is n login.
Everyone understood how we calculated 10 n login?
Tell me one thing, very starting itself, while inserting itself, we have to do proper, like
What?
sorting, right? See, I'm inserting into I'm putting the value in heap. That time it's we are doing this sorting. Sorting in the sense EP5.
Yes. So we inserting that time we did yes.
Okay.
So every time so as simple as we know how to insert. We have 10 million values, and every time we take value, insert into heap, next value, insert into heap. So first time composite log of 1, log of 2, log of 3, log of 4. So total sum will be log of 1 plus 2, log of 2 plus log of 3 till log of n, and hence total will be n log n. Worst case n log n. Okay? So we have n log n to insert, and we have 10 log n to find the top 10. Correct? 10 log n to find the top 10. Correct? That's what you're saying? Yeah. So this is okay. This will work. But now that I have given you just 10 elements, or just top k elements, where k is much smaller than your n. So suppose there is 10 million products. I just want 10 products. I just want 10 products. Top 10 products. How will you improve this to better, make it better? I don't want million log million. I want something better. Why did you even use? Why did you even use your heap? If you wanted to do same, that thing only. You could have simply 10k. Find that smallest element, done. Find the second smallest element, done. Find third smallest element, done. So at the end you'll have 10 times. It will be 10. If you talk this top k elements, okay. I'm just not talking in terms of k now. So you can simply do top smallest element, then second smallest element, third smallest element, and keep on finding till k. So you'll have a total of k into n. Total k n it will be. होगा ना, k n होगा ना. If you do that, and by your method, it will be n log n, which is not something good than k n. By the way you solved was, it was n log n. So n log n is equal to which is better? Is n log n better or nk better? So what I'm trying to say is, if you don't use any heap and all, you can simply do first find the smallest element, second smallest element, third smallest element, just until k smallest element. How much time that will take? That will take k of n, nk. And if you do by your method, which was insert all the elements into a heap and then take out one by one, it will be n log n. So which is better? N log n is better, or nk is better? Where k is much smaller than n.
Yeah, nk is better.
Both are almost equivalent. Okay, both are almost equivalent. So but it depends what is the value of k. But I'm saying even after using a heap and all, you are still very close to nk. You have just improved n log n. So what is the use of using heap? You're using heap. You should get more benefit of heap rather than just such a small benefit. Think again. This is a very standard question. I have in my interview lifetime, I have been asked this question multiple times. We are learning about heap, and this is a heap question. So much of hint, so much of context. Interviews would be contextless. No idea where he's asking from. Okay, so you have to crack even tougher situations in interview. This is every knowledge you have. You have to use a heap, and then you have to find the solution. I'll be back again. Think.
हेलो
क्या क्वेश्चन था?
What is
हाँ क्या what is the question?
what is the question?
I think same question is asking us to improve on the solution.
Yeah, instead of
Login.
tell me one thing. If we sort anything, then we need to iterate.
Yeah, even if you sort by other techniques, it will be n log n.
Login. Yeah, even I'm thinking that way. Oh my god.
Yes. Anyone?
क्वेश्चन क्या था सर?
But question is you have to find the top k element out of n products. Top k product out of top k selling product out of n products, and in a time better than n log n or nk.
Okay.
ठीक है, छोड़ो अब बता रहा हूँ. So again coming back to what you were doing was you were inserting all the elements into your heap and then taking out the top k one by one. Okay, delete minimum k times. Hence it was insertion time was so bad that you didn't even care about the deletion time. The insertion was only n log n. So what you can do is, instead of maintaining a heap of size n, why don't you just maintain a heap of size k only? So what you can do is you can maintain a max heap. Okay, maintain a max heap or min heap. Let me think. So we want to find the top k product, which is having the top k means the one we got sold maximum number of times. So if we have a min heap or a max heap, which we'll take. Let me think. So if you take a max heap, then we want top element max heap min heap है. So we take a min heap if it is more. Yeah, let's take a min heap. Okay, min heap. So we maintain a min heap of size k, not n, size k. We take first element from the first product and check the count. Is the count more than the topmost element in the heap? Yes, then insert. Otherwise, if it is less, ignore. Take the next element. Is it more? Then insert. So first k element will go into the heap. Okay, first k element will go into the heap. The k plus now after that, each element we compare. Is it less or more? If it is more, then that is a contender of top k. So it should go and topmost will come out. Delete minimum and insert this. It's like just insert the new element. So we have this k, top k every time. At every point of time, we have top k till that point of time. We just take the next element, again compare with the topmost. Is it more or less? If it is less than minimum, just ignore that, go ahead. If it is more than minimum, then since it's the min heap, so topmost element will be the smallest among all of them. So just try to insert that element and remove the topmost element. So we have this heap of elements, top k elements at every point of time. We just go to next element, compare with the heap. अगर वो topmost से ज़्यादा है, इसका मतलब that is the contender of the top k, and the topmost element should go out. So just remove the topmost and insert the new element. Otherwise, just ignore. Hence, you just do the same operation for all the elements, and at the end of this, you have your top k elements. समझ आ गया? क्या हुआ?
Yes.
समझ आया क्या? So we are maintaining top k only. We don't have to maintain all top in our heap. We don't have to maintain all n. Just maintain top k, because if you maintain top k in a min heap, the point is min heap. We want to maintain a top k, but we are using a min heap. Why? Because I want to keep my minimum element at the top, so that I can compare the element which is it the contender or not. I just compare with the topmost element, and that will take a constant time comparison. If you suppose we use some other structure, suppose we maintain an array of top k elements, and every element, so we have this array of k elements. We go to the next element and compare, and we want to decide whether this new element is it bigger than my the smallest element or not, or then we have to compare in the array, find the minimum element and compare and all. So that's why we maintain a heap, so that we can simply compare in constant time whether the new element which we are considering is it bigger than the root element or not. If it is bigger, then just insert that. If it is not bigger, then just ignore that. So by doing this, how much time do you take this time? What is the time complexity this time? Finding the top k. What is the time complexity, Nitesh?
Finding the top k.
Yeah, this new algorithm which I just told.
It will be k log k.
N log k.
K.
N log k, not k log k. We are doing for all the n elements. We're not skipping an element. We are doing for all the elements. Earlier also we were doing for all the elements, but it was n log n. Now it will be n log k, not k log k.
No, but we are keeping only k in our heap, right?
K elements. Yes.
Yes.
So if we have a like heap of k size, then finding will be like deleting only, right? So the deleting is n log n. Then if the heap size is k, it will be k log k, right? And insertion will be n log k. So finally it will be n log k.
So we are inserting and maintaining top k at same time. We're not doing it separately.
Correct.
We're not doing it separately. Yeah.
Yeah. Finally it will be n log k.
N log k.
Yes. Finally.
Subhadeep. Yes.
For building a min heap, it will be k log k, correct?
Building. So yeah, this time we're not doing this operation separately. What we're doing is we're building the heap and finding the top k at the same time. So what is happening? Every time we just take element from the big array, which is an element. We take one element, we insert it into our heap, which has not been built or building, whatever. We have this heap maintained. So initially it will be 0 elements. Then we just have to insert, and parallelly we have checked for that k element. Okay. Now we take k plus 1 element and check in that heap. So we're not doing separately. Even if you're doing separately, yes, you're right. K log k to create and then n log k to do. Yes, but we're not doing it separately. We are in the same flow only. We take one element from the array, build check in the heap. Take the second element, check the heap. Initially the heap size would be 0, 1, 2, 3, 4, and at the end it will be k, and the size will still remain k for all the elements. So what I'm trying to say is we're not doing it separately like we did for previously, the separate process. One was insertion and one was deletion. Here we are just inserting, and that to deciding whether to insert or not. We're not deleting anything. I mean, we're deleting because we're inserting. Size is exceeding that. That's why deleting. But what we're doing is we just take one element and check in the heap whether should we insert or not. So we are inserting only few of the time, only k times, but the rest of the time we're just comparing. So that comparison is taking n times. You're doing it n times, n into by the way, it won't be even n log k. If you think properly, it won't even be n log k. It will be 1 plus 1 plus 1 plus log 1. What I want to say is only k times you will be insert. No, sorry. You can have to. Sorry, it will be n log k. I have known. So every time you take elements, the worst case can be every element you take, you insert and remove. Every element you take, you insert and remove. So in the case where all your top k elements are at the last index, like it is sorted in the ascending order. So you first insert 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the 11th element is bigger. So you insert 11, remove 1. Then you insert 12, remove 2. Then you insert 13, remove 3. And like this, if your array, if you're already sorted, in that case, finding the top 10 using this method will be very bad. It will be n log k. Okay.
Yeah, Praveen, your question is where we are inserting, at the root or at the last position, the kth position.
So we compare with the root, and if it is bigger than root, it can go anywhere in the heap, wherever it is suitable position is. Again, inserting a heap, we don't define where position should be. It's like whichever is it can be suited at only one position, not only one, but it has a suitable position. There we'll insert. Where it's not necessarily be inserted at the last or it will insert at the first. It has to be inserted at the correct position to maintain the heap property.
No, that's correct. But initially, we need to insert and do some mini EP5 something, right, to put it in proper.
Yes.
So each time once we insert, then we need to check that EP5 something or what to put it properly.
No, so insert method is internally calling heapify. We don't do separate heapify. Insert itself is calling heapify internally. We know that insert method is a proper method. Insert method is an abstract method which does its work. It properly implements insertion. It inserts, it does heapify, whatever. We don't have to again call heapify separately. Why do you want heapify is a utility method for insertion and deletion. We don't have to do heapify ourselves unnecessarily. So when you just call insertion method, insert 2, okay, insert 10, it will do whatever way we have told. Okay, it will insert the new element at the last place, and then it will call those reverse heapify or whatever. So
Okay.
We don't have to separately call heapify.
Okay, got it.
Okay. So we have improved from n log n to n log k. Okay, where again I said k was very small number, hence this would be improvement. Okay, and also we don't have to maintain this complete size in complete detail into another heap of size n. We just have to need a heap of size just k. Okay, so it has a
memory has improved. That is a big plus.
Yes, so we have improved upon time as well as space. We don't have to store all the number again into a heap. Okay. Okay, let's then move to the next question, which is kth smallest element in the array. This is something similar. I hope you can just tell me 1 minute. How will you find the kth smallest element in an array?
We can have a heap of k size, min heap of k size, and after passing the entire our n elements.
Yes.
At the end, whatever will be root of the heap will be the kth smallest element in the array, right?
Are you sure you'll use min heap? Thing. So you maintain a heap, correct? So you maintain a heap, that is correct. You want to find the kth smallest. Kth smallest. So if I maintain a max heap of k elements, then topmost element will be the highest of those smaller elements.
Yeah.
Highest of those smaller elements. So topmost element will be the kth element. Subhadeep, समझ में आया क्या बोला मैंने?
हाँ.
So we maintain, to find the kth element. So this is the trick part here. You have to find the kth smallest element. So out of 100 elements, the 9th smallest is is from the like ninth element. So that's a very simple case. So I want the smallest k smallest. Okay, not the small, but k smallest. So he was saying that he will use a mini. But if you think properly, what we want to do is we want the k smallest. So if I maintain the k smallest, so just the topmost element of the k smallest element, just the so just the topmost element of the k smallest element is the k smallest element. So if you maintain a max heap where we are storing all the k smallest element, then the maximum element is what we want to find. Again, I'll repeat
Praveen,
clearly. Yes.
so I was thinking if we are maintaining a max heap,
Mhm.
uh,
Max
yeah,
heap of
fine.
smaller elements. Max heap of smaller elements. Okay, max heap of smaller elements. So what will happen is we have all the smallest elements in our max heap now. Now, which is the k smallest? That one at the top is the k smallest, because all the smallest are in this heap only, and the k is, and for sure the topmost is the maximum among them. So kth element, k smallest, is the topmost element of this max heap. If I ask you about the kth largest, how will you implement, Subodhi? Kth largest?
Same like we'll build a max heap and
We'll build a min heap.
minute. Sorry, minute.
We'll build a min heap of larger elements. Then the topmost element will be the kth largest element, because we have a min heap where all the values, larger values are stored. So the topmost element will be the smallest among all those larger elements, and we want the kth largest. So topmost element will be the kth largest. Okay. Last question. Vasant, समझ में आ गया?
Yeah, but while doing comparison, we need to compare like if the root is greater than less
Yes. So while finding the top k or bottom k, largest k or smallest k, when you go through iterate through the array, whether you have to compare if the current element is more than the topmost element or less than the topmost element. That comparison you have to think. Okay, and I think you can think logically. Okay.
Okay.
Yeah. So last question is merge k sorted arrays. You have been giving k there are k sorted array. You have to merge them into single. Sorry, just a second. Not Go ahead. Merge k sorted array. How will you?
Merge k sorted array.
Yes.
Praveen,
Hmm.
one quick solution I can think, we can have one heap where we can push all the elements of all the arrays, and then we can pull out.
Okay. So what will the
But
complexity then?
I think that will be very huge.
That is not so good solution. So what will the time complexity of that? Can you think?
It will be n log n only.
Okay, yeah, but correct. So think something better now. Okay, so take that as an assignment, and we'll just end here with this last thing which Subodhip had an issue with. He was not able to get this thing properly. What is this code doing here? Subodhip?
Yes.
Yeah. So Subodhip, if you see what he's doing, he's adding an edge to a adjacency list matrix. Adjacency list graph. So we have this adjacency list. Okay. So what we're doing is for every time we want to insert add a new edge between source and the destination. What we do is this 3-step is clear. Okay, what we do is we first create a node, destination node, which is new adjacency node. We create this node first. Once we have created, we insert this new node which we just created. New node dot next is equal to the graph's source dot head, the first element in the graph in that list. So we have this. I'll try to draw this list. We have this node 1, we have this node 2, 3 like this, and at every node we have this linked list maintained. Some 3 and then 4. Suppose this was maintained, and then we had this maintained. So okay, something like this is maintained. So what we do is we create. We want to add an edge called 5 to 6. Okay, this is the edge we want to add. So what we do, or suppose 5 6 already there. Suppose we want to add a new edge. This is already there. I want to add an edge 5 to 8. Okay, 5 8. I want to add an edge 5 8. So what we do is we first create that 8. So 8 is created, and after that we bring 8 at the head of this list. So this is the list. This, if you see this part of graph of array of source, graph of array of 5 is a list. So you just make 8 ka next is equal to 6. This is what we're doing here in this line. Node next is equal to graph array of source, like which is graph of array of 5, which is equal to 6. You just point 8 to 6. Once you point 8 to 6, you just change your graph of array again. Head. You point your head to 8 now. You point your 5 to this now. So your new list is 5 8 from 5, which is the list is 8 6 and 7. So this is what we're doing here. This is a very simple step. If you try to analyze slowly, it's not something complicated. And this other part which is here written is, since this is an undirected graph. Yeah.
Okay. But अच्छा undirected इसलिए उल्टा edge लगा रहा है, correct?
Yeah. So just like we can maintain this for our undirected tree, we have to maintain one more edges. All the reverse is also there. Just maintaining one more reverse edge also. So he's adding from 8 to 6 we added edge. From 6 to 8 also we will add an edge. That's it. That's what he's doing.
So basically maintaining 2 edges between 2 vertices.
So this edge, we can't maintain an edge here since it is a list. So somewhere else 8 was there, somewhere else 8 was there, and there was a list at 8 also. So there also he's inserting. Suppose there was 8, at 8 we had 9, and 9 and 10 suppose. So we have to insert this 5. We have to insert this 5 at this position 8 also. So that's what this part is doing. Insert 5 where the 8 is source. So first insert 8 where 5 is source, and then insert 5 where 8 is source. Both the same thing we're repeating. Here one time the source is 5, and here one time source is 8. So both the times find the source whichever you want to consider source, and then insert the other one into the list which is contained there. Okay.
ये लास्ट 3 लाइन समझ में नहीं आ रहा था कि अभी पॉइंट आउट किए अनडायरेक्टेड और इसीलिए.
Yes. Okay, so this is a very small assignment I've given you. It's not a big assignment. Now I'm done with all the data structures. I will cover few algorithms, but I'll try to do lots of questions. I'll just paste questions now. Okay, and you have to just do at least, I've been telling you, you have to do practice questions. You people not practicing, so this will only be bad for you. So I'll try to give some question, but you have to practice. And the very simple. There are only 2 sites: lead code and gigs for gigs. There are not lots of places you have to run. I'll also pick from these places only. It's not that I'll create questions. I'll also pick from these places only. But still, I'll try to give questions. you have to start practicing as much as possible. ठीक है?
Yes.
चलो, okay then. Bye bye.
Good night.
Good night.